In the silent heart of a neutron star, matter becomes stranger than any everyday solid or liquid. Pressure builds layer by layer until the rules of stability reach their final edge. Tonight's journey moves through superfluid cause-phase boundaries and the quiet constraints that decide what can endure. If this kind of calm, deep science helps you unwind, please tap like and subscribe for more long-form sleep documentaries. New episodes arrive with gentle pacing, clear imagery, and steady narration. Now let the darkness settle and let the story begin. The core of a neutron star feels like a quiet place where ordinary pressure loses meaning. The early anchor is that immense compression forces matter into collective states while the surface stays smooth. A dark sphere hangs against a sparse starfield. Its limb shows a thin rim of bent light. A soft gradient runs from grey into black. The object spans about 20 kilometers. It is like the width of a large lake. Inside that small space, gravity stacks layer upon layer until the interior behaves as one connected medium. A clear consequence appears quickly. The star does not keep shrinking because resistance rises from the rules of crowded matter. Degeneracy pressure means particles resist sharing the same allowed states. Compression stops being a squeeze of grains and becomes a squeeze of possibilities. In the cutaway view, the outer crust appears as a thin shell with a sharp boundary. Below it, the density darkens in smooth bands like snow crystals pressed into glacier ice. Loose grains become a locked sheet without heat and without melting. The same calm transformation happens here, but on a scale set by gravity. Pressure builds without the agitation of warmth. The interior stays cold by ordinary standards, yet the resistance remains immense. Another simple consequence follows. Support can come from quantum crowding rather than from thermal motion. The surface shadow line remains steady even as the deeper bands tighten. Another consequence appears as the crust gives way. At higher density, nuclei stretch and lose their familiar shapes. The boundary becomes a patterned region of slabs and rods. Edges repeat and then fade. The structure looks like layered ridges in compressed ice where cracks flatten into seams. This physical detail matters because it changes how stress can spread. It also sets the stage for motion without obvious surface change. A gentle scale shift follows. The shapes begin at the scale of particles, yet they can fill a region kilometers deep. From far away, the star still looks like a polished bead. Inside the layers resemble stacked strata with subtle curvature. Another visual anchor forms along the gradient. Darkness deepens smoothly rather than in steps. It is like a glacier cross-section, where trapped bubbles thin with depth. A deeper change appears with the next concept. Deep in the fluid interior, many neutrons pair and move in step. Superfluidity is flow with almost no internal friction. Motion can become smoother as density rises. Energy that would become heat in a normal fluid can remain stored in ordered motion. This change alters the sense of what a core can be. Instead of turbulent boiling, the interior can be a disciplined flow. The visual anchor slows at rotation. The star spins, and the superfluid cannot swirl in just any way. Rotation organizes into many thin vortices. Each vortex is a narrow core where flow circles an almost empty center. The array of vortices aligns like hair-fine lines through the dark interior. Here, a quiet stability becomes clear. Large-scale rotation can persist because the interior keeps spin in a tidy lattice of threads. Those threads do not stay fixed forever. They can drift slowly through the superfluid. They can meet imperfections near the crust and become temporarily held. When that hold relaxes, the global rhythm can adjust in a small step and then settle again. Microscopic structure links to the macroscopic rhythm. The image remains calm. Within the cutaway, the threads look like faint scratches in dark ice. Near the seam, some threads bend and gather. The gathering is sparse and orderly. It resembles streamlines that curve around a buried ridge under snow. A further scale shift follows. A single vortex core is tiny, yet a forest of vortices can span the star from pole to pole. The organized pattern lets the star carry rotation with minimal loss. A new scene lingers on its shape. Rotation can give the star a faint equatorial bulge. The bulge is subtle and smooth. It is a physical reminder that even dense matter yields to steady turning. Another consequence appears where textures meet. A seam sits between the stiff crust and the smoother reservoir below. Along that seam shear can build and then relax. The change is small and gradual. It resembles the slow settling of a glacier face after a distant shift. Tension releases along a hidden plane. This seam offers a simple function. It lets different layers trade angular momentum without a violent scrape. The cutaway image shows the seam as a faint ring. It is not bright. It is a boundary in behavior rather than a border in color. A limit of intuition appears with pressure itself. Everyday experience treats pressure as weight on a surface. In this core, pressure is also the cost of forcing quantum states into tighter ranges. Ordinary images fail because the material is not a simple solid or liquid. It is a quantum crowd acting as one. A limit of observation follows and it stays precise. No direct pattern of light can map the deepest core layer by layer. Only global effects escape. Gravity sets the star's size and its curvature. Spin sets a rhythm that can drift and then settle. From these outside clues, the interior must be inferred. This indirect path sets a boundary on certainty. Different interiors can produce similar outward balance within finite precision. A final consequence closes the loop on the true limits. Gravity keeps adding load toward the center. Stability depends on how fast pressure stiffens as density rises. If the interior softens, support weakens and collapse becomes the natural outcome. If the interior stays stiff, the star holds a stable radius with quiet persistence. The superfluid and the layered seam influence this balance by changing how stress and heat redistribute over time. The cutaway image returns to the smooth shell and the deep dark bands. Pressure appears not as a single force, but as a layered response that changes character with depth. The next step is to linger on the crust and its boundaries as a calm map of transitions. From that map, the path inward becomes clearer without hurry. A neutron star crust looks still, yet it is a stressed shell that carries the first signatures of the interior. The early anchor is that a thin, solid layer shapes how the whole star holds strain and passes changes inward. At this distance, the surface appears smooth and dark. A narrow rim of bent light traces the limb. Beneath that calm outline, the crust forms a hard skin only about 1 kilometer thick. It is like the depth of a large city from edge to center. That single kilometer matters because it is the star's stiffest boundary. It sets where brittle patterns can exist at all. It also decides how deep a motion can reach the outside without tearing the star apart. The first scene slows over a close cutaway. The topmost layer is a lattice of nuclei. Electrons flow through the gaps like an invisible sea. The lattice is not uniform. Pressure increases with depth and the spacing tightens. The physical detail is a gradient that steepens quickly. The lattice begins with near regular spacing. Deeper down, the pattern compresses into tighter rows. A small payoff appears in that simple shift. A solid can exist here because electron pressure supports the lattice. Heat does not need to do the work. The crust holds shape because quantum crowding props up the scaffold. Another visual anchor settles on the boundary where the crust changes character. A shadowed band marks the transition to denser layers. The band is not a painted stripe. It is a zone where the lattice stops looking like separate spheres. Nuclei begin to stretch. Shapes become rods and then slabs. The arrangement resembles layered sheets of wax pressed under a steady hand. This is the next unlock. When shapes elongate, the material becomes strong in one direction and weak in another. Stress travels along sheets more easily than across them. That anisotropy matters because it guides how the crust can crack or slip. The analogy stays everyday and unique. It's like stacking thin, slightly sticky cards and pressing down. The stack holds weight well, yet it can slide along the card faces with little effort. In the crust, the same idea appears as layers and seams. The star's gravity provides the press. The result is a crust that can store strain quietly. Another scale shift follows. The card thickness is tiny in daily life. Here, the layered zone spans a significant fraction of the crust. The transition is microscopic in its cause. It becomes macroscopic in its consequences. The next scene lingers on shape and motion. The star rotates and the crust must turn with it. The crust is rigid, yet it is not perfectly smooth inside. Small irregularities can pin deeper flow patterns at the boundary. The physical detail becomes a seam where the solid meets a more fluid interior. Along that seam, stress can accumulate. Another payoff arrives in a gentle way. The crust acts as a reservoir for strain. It can hold tension for long periods and release it in steps. Those steps do not need heat or chemical change. They come from mechanical thresholds in a compressed lattice. The idea becomes clearer with another image. A faint ring like a crease circles the cutaway at a constant depth. It marks where the lattice changes from more spherical shapes to more sheet-like shapes. That ring is not seen from outside. It is a boundary in behavior. A further consequence unfolds. When the crust stiffens, it affects the star's overall shape. It can support small deformations without flowing away. The star can remain slightly oblate from rotation. It can also carry small bumps in mass distribution. Those bumps matter because they change how the star responds to rotation. They also change how energy can be stored and then relaxed. The story remains calm. The crust is not a noisy skin. It is a quiet arch. It carries load and defines how the interior communicates with space. A limit of intuition appears with the idea of solidity. Solids on Earth are shaped by chemistry and temperature. Here, solidity is shaped by pressure and electron support. Ordinary intuition fails because the crust is not a rock made of molecules. It is a Coulomb lattice of nuclei in an electron background. A Coulomb lattice is nuclei held by electric forces. The definition is brief and then returns to plain language. It is like a grid of charged beads held in place by mutual attraction and repulsion. It is also like a net stretched by many small ties rather than one thick rope. It matters because it sets the crust's stiffness and its breaking style. A limit of observation follows and it stays specific. The crust thickness and composition cannot be mapped directly by any image. The layer boundaries are far too fine to resolve at distance. The inference must come from global effects like radius and mass. It also comes from timing changes in rotation. These are indirect clues with finite precision. Different crust models can fit the same outward measurements within uncertainty. That boundary uncertainty stays in place even when models are careful. Another visual anchor returns to the rim of bent light at the limb. Light behaves as if space is curved near the surface. The rim is thin and steady. It is a reminder that gravity dominates every layer. The crust is not a separate object. It is a boundary condition in a stronger field. The final calm transition forms. The next step is to move from this stiff shell into the deeper fluid, where friction can nearly vanish. From there, rotation and flow become the main language of the core. The interior beneath the crust feels calm because motion can become organized rather than turbulent. The early anchor is that many neutrons pair and flow together, allowing rotation to be carried by ordered threads. In that region, darkness deepens into a smooth gradient. The seam below the crust fades into a wide, dim reservoir. The boundary is not a sharp wall. It is a gradual change in stiffness and flow. The scene holds on the cutaway where faint lines run parallel to the rotation axis. Those lines are not cracks. They are the trace of vortices inside a superfluid. Superfluidity is flow with almost no internal friction. The definition stays short and then returns to plain language. It's like a river that slides without warming itself. It is also like mist moving through a narrow valley without swirling into foam. It matters because rotation can persist without being ground down into heat. A small payoff arrives with the first consequence. When friction almost vanishes, the interior does not need to churn to keep spinning. It can carry angular momentum in a tidy pattern. In a superfluid, rotation cannot be spread smoothly everywhere. It gathers into quantized vortices. A quantized vortex is a thin tube of circulating flow. The idea becomes clearer through one everyday analogy that stays unique. It is like a record player that cannot smear its grooves. Instead, it holds rotation in many fine circular tracks. The interior becomes a quiet library of those tracks. Each vortex is a single thread. Many threads together represent the star's spin. The visual anchor lingers on the arrangement. Vortices form a sparse forest of hair-thin lines. They run nearly straight through the fluid. Near boundaries, some lines bend slightly. The bends appear where the medium changes. The physical detail is curvature along a gradient of density. The gradient squeezes the vortex cores and changes their spacing. The spacing is not uniform. It becomes tighter deeper down where the fluid is denser. Another payoff arrives in that spacing. Denser region needs more vortices to represent the same rotation rate. The star's interior therefore carries a map of density in the pattern of its threads. That map is not written in light, it is written in flow. The scene slows again. A faint ring in the cutaway marks where vortices approach the crustal seam. The ring is not a surface feature. It is a meeting zone where different kinds of matter touch. The seam offers imperfections and stiffness changes. Vortices can become pinned there. Pinning means a vortex line is held in place by a defect. The definition stays brief and then returns to plain language. It is like a thread snagging on a rough patch. It is also like a fine hair catching on a seam in fabric. It matters because stored rotation can become temporarily locked. Another small payoff follows. When pinning holds the crust and the superfluid can spin at slightly different rates, the difference builds quietly. When the hold relaxes, vortices can slip and redistribute. The star's rotation can adjust in a step and then settle. The adjustment is gentle in this telling. It is a mechanical release rather than a dramatic event. The visual anchor stays steady on the forest of threads. Some lines drift. Some remain anchored near the seam. The drift is slow and smooth. It resembles pollen grains moving in a still pond. The motion is ordered because friction is low. A scale shift softens the picture. A single vortex core is tiny compared with any grain of sand. Yet the collective array spans the star's full depth. A microscopic rule becomes a macroscopic rhythm. The one primary number in this section stays simple. The vortex spacing is often about a millimeter. It is like the thickness of a coin. That millimeter scale repeats across a region that is tens of kilometers wide. The contrast is gentle and clear. Tiny spacing carries the burden of a whole star's spin. Another payoff arrives from that contrast. The star can change its global rotation without melting or breaking the whole interior. It can do so by shifting the count and placement of vortices. The adjustment is like rethreading a loom by moving a few strands. The loom remains intact, the pattern changes, the physical details keep grounding the image. The cutaway shows a smooth density gradient like a deepening twilight. Vortex lines remain nearly parallel. Their slight waviness appears where pinning and unpinning compete. The boundary region shows faint layering from the crust above. This layering sets the landscape that vortices navigate. The section now touches the limit of intuition. In everyday fluids, friction is always present. Motion becomes heat and then fades. Here the intuition fails because the fluid is quantum coherent. The flow can persist without internal damping for very long times. That long persistence is outside ordinary experience. The section also touches the limit of observation and names it precisely. No direct image can reveal the vortex forest in the core. The threads do not emit light. The inference must come from how rotation changes over time. It also comes from how the star's shape responds to spin. These are indirect signals with limited resolution. Many different interior pinning strengths can match the same outward timing within uncertainty. That limitation sets a boundary on claims about exact vortex behavior. Another visual anchor appears to keep the cadence slow. Light behaves as if it grazes the star and wraps around the limb. The rim remains thin and pale. The outside stays calm while the inside carries a hidden lattice of motion. Another payoff follows from that contrast. The star can look perfectly steady while its interior rearranges. The rearrangement is not chaos. It is a controlled migration of quantized threads. The migration changes how stress is shared between crust and core. Over long intervals, the crust can be gently stressed and gently relieved by this exchange. The section returns to the unique analogy of grooves and tracks. Rotation is stored in discrete lines rather than smeared motion. That discrete storage makes the interior behave like a structured medium. It also prepares the next transition. Deeper layers may change the nature of the fluid itself. If matter softens or transforms the rules for vortices, and pinning can change with it. The closing sentences remain soft. The next step is to follow the density gradient farther down. From there, the question becomes which phase of matter sets the deepest stiffness and the true limit of pressure. A superfluid core stays smooth only when it can share motion with the solid crust without grinding itself into heat. The early anchor is that a weak but persistent coupling lets the crust and core trade rotation through tiny forces on vortex lines. At this distance, the star remains a dark bead with a thin rim of bent light. Inside the cutaway, a broad band of fluid sits under the rigid shell. The band is not uniform. A gentle gradient of density darkens toward the center. The visual anchor settles on a quiet shear layer. In that layer, vortex lines tilt slightly and fan outward. The fan is subtle and orderly. It looks like long grass laid in one direction by a steady current. This slow geometry answers a first question. A superfluid can carry rotation, yet it still needs a way to feel the crust. That feeling arrives through the vortex lines themselves. Each line is a place where the superfluid circulates strongly. Around each line, other components can interact. A small payoff appears in the simplest form. Coupling is not a bulk drag across the whole fluid. It is a set of contacts concentrated along many thin threads. The first concept is entrainment. Entrainment is partial commotion between neutrons and the lattice. The definition stays brief and then returns to plain language. It is like fine silt that moves with a riverbed rather than with the open flow. It is also like frost that clings to a branch and shifts only when the branch shifts. It matters because some of the neutron fluid behaves as if it carries extra inertia. That changes how easily rotation can move between layers. The cutaway image shows the crustal base as faint strata. Just below the fluid appears darker and smoother. The boundary is not a crack. It is a zone where the lattice fades and free motion grows. In that zone, entrainment is strongest. The next small payoff arrives. A strongly entrained region makes the crust feel heavier than its mass alone. Rotation stored in the fluid is not fully separate. It partly follows the solid pattern. That means a change in the crust can tug on the fluid without direct friction. Another visual anchor appears to keep cadence slow. A ring-shaped contour inside the star marks where the shear is steepest. Along that contour, the vortex fan becomes denser. The density is a physical detail that matters. Where the fan is denser, more vortex lines cross a given area. More lines mean more contact points for coupling. The second concept is mutual friction. Mutual friction is drag between vortices and the normal component. The definition stays brief and then returns to plain language. It is like burrs catching on fur as wind carries seeds past. It is also like dew beads that resist sliding on a leaf edge. It matters because it sets the rate at which the differential rotation can fade. The analogy remains unique. It avoids gears and machines. It stays in natural textures and gentle contact. The key detail is that drag acts on the vortices, not on empty space. The star therefore couples through a sparse network rather than through a uniform viscosity. A single number anchors the scale in calm words. Only about 1 part in 1,000 of the interior acts as a normal component at a given moment. It is like one bright grain among 1,000 grains of sand. That small fraction is enough because vortices provide many places for interaction. Another payoff appears from that. A tiny normal fraction can still control the long-term sharing of angular momentum. The sharing does not need a large reservoir of ordinary fluid. It needs a pathway for momentum exchange. Vortices supply that pathway. The visual anchor returns to the tilted lines. Each line is straight through most of the core. Near the boundary, a line bends and then straightens again. The bend is a physical response to changing stiffness and density. The bend also marks where mutual friction can act more strongly. In that region, the normal fraction can scatter off the vortex cores. It can also interact with magnetic structures trapped in the fluid. The wording stays careful. The key point is not the microscopic detail. The key point is that coupling strength depends on what lies near each vortex. Another small payoff follows. If coupling is weak, the crust can drift ahead in rotation. If coupling is strong, the crust and core stay nearly locked. The star's rotation history therefore carries a fingerprint of the coupling. That fingerprint is soft and indirect. It does not require a violent signal. It can appear as gradual relaxation after a small step in spin. It can appear as a gentle change in how stable the rhythm remains. A scale shift keeps the narrative calm. The interactions happen on the scale of vortex cores. That scale is far smaller than any dust mote, yet the effect reshapes the rotation of an object tens of kilometers wide. A microscopic drag becomes a global settling. The cutaway image widens, the star's outline stays smooth. The interior shows bands like faint smoke layers in still air. The layers do not swirl, they drift in ordered alignment with the rotation axis. Another visual anchor appears to maintain the sleep rhythm. A narrow boundary zone looks slightly brighter in the cutaway. It is brighter only in illustration. It marks the place where shear concentrates. Within that zone, vortex lines cluster into a gentle comb pattern. The comb pattern is steady. It suggests persistence rather than turbulence. The limit of intuition arrives with a quiet clarity. In everyday fluids, friction is a property of the fluid itself. Here, friction is an emergent effect tied to vortices and rare excitations. Ordinary images of syrup or water fail. The core is neither thick nor thin in the usual sense. It is a coherent medium that only resists change through specific channels. The limit of observation follows and names its boundary. No direct measurement can map entrainment or mutual friction deep inside. The interior cannot be resolved layer by layer by one light signal. The only clues come from outside timing and global shape. Those clues have finite precision and model dependence. Different coupling strengths can produce similar outward behavior within uncertainties. That is a concrete limit on inference rather than a lack of effort. Another payoff arrives from accepting that limit. Rather than seeking a perfect map, the task becomes narrowing. Families of interiors that match stable patterns. Coupling becomes one control knob in that family. The vortex fan becomes a visual shorthand for that knob. A wider fan suggests a region where lines are more mobile. A tighter fan suggests a region where lines are more constrained. The section eases toward its close. Entrainment sets how much of the neutron fluid effectively joins the crust. Mutual friction sets how quickly differences in rotation are erased. Together, they form a quiet bridge between solid and superfluid. The next step is to go deeper into the pressure rulebook that decides which phases can exist at all. From that deeper rulebook, the true limits of compression begin to appear. Pressure in a neutron star core behaves like a quiet rulebook that decides which forms of matter can exist. The early anchor is that the equation of state links density to stiffness and sets the star's size for a given mass. In that region, darkness deepens without any sharp edge. A smooth gradient runs inward like twilight deepening toward night. The cutaway shows nested layers. Each layer is not a different substance by color. Each layer is a different response to compression. The visual anchor holds on a set of faint contour rings. The rings mark equal density surfaces. They look like soft ripples frozen inside a dark sphere. The first small payoff comes quickly. If the inner layers stiffen rapidly, the star resists further squeezing. If they soften, gravity gains ground and the radius shrinks. This is the simplest way the hidden rulebook reaches the outside. The outside does not show the rulebook directly. It shows the outcome in size and curvature. The core concept is the equation of state. The equation of state is the pressure-density relationship of matter. The definition stays brief and then returns to plain language. It is like a recipe that sets texture as ingredients are packed. It is also like a mattress chart that maps weight to sag depth. It matters because the same mass can make different radii depending on this mapping. The analogy stays unique and quiet. It avoids pumps and machines. It stays with texture and support. The scene continues with physical detail. Along each contour ring, material conditions remain similar. Between rings, conditions change and the response stiffens or softens. The rings are closer together toward the center. That closeness is the visible sign of a steepening gradient. Another payoff arrives from ring spacing. Tight ring spacing means density changes rapidly with depth. Rapid change means the inner structure strongly affects global balance. A slight shift in the core can alter the overall radius. The section's single number anchors the scale in calm words. The star's radius is about 12 kilometers. It's like the length of a long bridge. That distance is small on cosmic scales, yet it contains the full gradient from crust to core. The scale shift becomes gentle. A journey of meters in the crust corresponds to huge changes in density. A journey of kilometers inward corresponds to changes in the fundamental state of matter. The cutaway view makes this readable without equations. The contour rings become a ladder of conditions. Another visual anchor appears to keep the cadence steady. Light behaves as if it bends around the limb and reveals a thin, bright rim. The rim is an outer effect of the same gravity that compresses the interior. A signal would carry that curvature outward as timing and redshift. The deeper rulebook leaves traces through the field itself. Another payoff follows from that link. Measuring mass and radius narrows the possible stiffness of the inner layers. A stiff core supports a larger radius. A soft core supports a smaller one. This is not perfect identification. It is a narrowing of families. The story remains calm and incremental. The section now adds a second concept that stays within limits. Phase transition means matter changes state under pressure. The definition stays short and then returns to plain language. It is like foam that suddenly becomes a compact sheet. It is also like wax that changes feel when pressed into a denser form. It matters because a transition can soften the equation of state over a range of depth. The cutaway rings show where such a change might sit. A subtle kink in ring spacing appears. Rings that were evenly spaced become slightly closer. The physical detail is a compression band where density increases faster for the same pressure increase. That band is not a crack. It is a smooth zone. It is a place where stiffness dips. Another payoff arrives from that dip. A dip in stiffness can limit the maximum mass the star can hold before collapse. The maximum is not fixed by surface appearance. It is fixed by the deepest response. The section avoids intense suspense. It treats the limit as a gentle boundary condition. The visual anchor returns to the contour rings and the quiet kink. The kink is the core's way of marking a transition without light. The next scale shift stretches time. These interiors remain in place for millions of years. The rotation may change. The crust may adjust. The pressure rulebook remains the same unless composition changes. That timescale makes the star a stable laboratory of extreme matter. Another payoff follows from the long time. Because the star persists, small differences in stiffness can shape its slow evolution. Cooling and rotation changes can reveal how easily layers exchange energy and momentum. These are subtle clues. They are not direct images. The limit of observation now becomes explicit and precise. The equation of state cannot be measured directly at the core. Only a few global quantities are accessible. Mass is inferred through orbital effects. Radius is inferred through surface emission modeling. Both carry systematic uncertainties. Different models of surface layers can shift the inferred radius. This creates a boundary uncertainty about the core. Even perfect measurements of a few quantities cannot uniquely select one interior. That is the limit of inference from low-dimensional data. The limit of intuition follows in a softer way. Pressure in daily life is a force spread over area. Here, pressure is also the cost of rearranging quantum states and interactions. Ordinary intuition fails because adding density changes which degrees of freedom can respond. Matter does not simply compress like a spring. It can change its internal structure and its stiffness. This is why the rulebook metaphor holds. The rulebook changes chapter as depth increases. Another visual anchor appears to keep the sleep rhythm consistent. The cutaway shows the contour rings fading toward a nearly uniform dark center. The fading is not emptiness. It is a region where gradients become harder to distinguish in a simple picture. The core is still structured by physics. It is just not easily drawn in sharp borders. Another payoff follows from this. If borders are smooth, the star can adjust without sudden failure. If a transition is sharp, stresses and coupling can behave differently. Smoothness or sharpness matters for how rotation changes. Relax. It also matters for how oscillations would travel. The section ends with a calm handoff. The next step is to examine what happens when density climbs high enough that particle identities may blur. From that threshold, the possibility of quark matter enters as a gentle question about stiffness and limits. Deeper inside, the core becomes quiet in a different way because the idea of a separate neutron begins to blur. The early anchor is that extreme density can unlock deconfinement where quarks are no longer bound inside individual nucleons. In that region, the cutaway darkens into a nearly uniform shade. The contour rings that were distinct become softer. Their spacing tightens toward the center. A smooth gradient replaces clear boundaries. The visual anchor settles on a transition band. The band is not a sharp line. It is a wide zone where the texture changes from grain-like to glass-like. The first small payoff arrives with a simple shift in meaning. At low density, matter is a crowd of particles. At higher density, matter becomes a medium with shared degrees of freedom. The star does not need to heat up for this. Pressure alone can reorder what is allowed. The first concept is deconfinement. Deconfinement is quarks no longer trapped inside one nucleon. The definition stays brief and then returns to plain language. It is like letters loosening from sealed envelopes. It's also like dye that stops staying in separate drops and becomes a continuous tint. It matters because the core's stiffness can change when the basic carriers of pressure change. The analogy stays unique. It avoids glass and ink used before. It stays with envelopes and dye fields. The cutaway shows the transition band as a gentle haze. Above it, layers still feel segmented. Below it, the interior looks smoother. The physical detail is a fading of microstructure into a uniform field. Another payoff follows. A uniform field can respond differently to compression. It may soften at first because a new way to pack matter opens. It may stiffen later as interactions between the new components become dominant. This is how the same process can both threaten and restore support against gravity. The next visual anchor slows on the inner contours. The contours appear like faint ripples in deep water that never breaks into waves. The ripples are closer together near the center. That closeness signals a rapid change in density with depth. A scale shift becomes gentle and clear. The transition is controlled by lengths far smaller than any dust grain. Yet the effect can occupy a region kilometers wide. A microscopic change in binding becomes a macroscopic change in how the star holds itself up. The one primary number in this section stays safe and round. The core density can reach about 1 billion tons in a cubic centimeter. It is like compressing a mountain into a sugar cube. The comparison is immediate and concrete. It also explains why separate particles begin to lose their individuality. Space between them becomes so small that boundaries overlap. The next small payoff comes from this compression image. When boundaries overlap, the cost of keeping quarks confined can rise. Allowing quarks to share space can become the lower energy arrangement. This is not a certainty for every model. It is a plausible chapter in the rulebook. The story stays calm and conditional. The second concept is quark matter. Quark matter is dense matter where quarks move in a shared medium. The definition stays brief and returns to plain language. It is like sand grains losing edges and becoming a continuous dune face. It is also like a crowd that becomes a single slow current. It matters because pressure can be carried by different particles and interactions. The cutaway image adds a new physical detail. In the transition band, a faint mottled texture appears. It looks like a fog bank with slow swirls. The mottling represents mixed phases. Some regions remain nucleon-like, some regions become quark-rich. The boundary between them is not sharp. It is a patchwork of domains. Another payoff arrives from that patchwork. A mixed phase can smooth the transition in stiffness. Smoothing reduces sudden jumps in density. It can help the star remain stable across a range of central pressures. This patchwork also affects transport. It can change how heat moves and how magnetic structure drifts. These are quiet consequences that do not need spectacle. Another visual anchor appears to keep cadence even. The inner core is drawn as a darker sphere within the larger sphere. Between them, the transition band glows slightly in illustration. It glows only to guide the eye. In reality, it is invisible. The glow stands for a change in response. The section now touches the limit of intuition. Everyday experience treats matter as made of objects with edges. Here, edges become negotiable. Keeping edges costs energy. Removing edges can be favored by pressure. This breaks the habit of imagining hard spheres packed tighter and tighter. The medium behaves more like a field than like a pile of marbles. The limit of observation follows and names its boundary. No direct measurement can confirm deconfinement inside a distant neutron star. Light from the surface cannot carry a detailed map of the interior composition. Only global properties and timing patterns can be measured. These measurements have uncertainties and model dependence. A soft equation of state with quark matter can mimic a nucleon-only model in some ranges. That degeneracy is a concrete limit on inference. Another payoff follows from accepting that limit. The goal becomes identifying ranges that are incompatible with stability. If a model softens too much, the star cannot support high masses. If it stays too stiff, the radius trends larger than allowed by some observations. The interior is therefore constrained indirectly by the mere existence of stable stars. The visual anchor returns to the ripples of equal density. In the mixed region, ripples blur. They spread like breath on cold glass. The blur suggests a smooth gradient rather than a sharp interface. This is a calm picture of a transition that does not need a sudden break. A further scale shift stretches time again. Once formed, such phases can persist for millions of years. They can cool and settle without changing composition quickly. The interior remains as a long-lived answer to pressure. The section closes with a gentle handoff. The next step is to examine how quark matter might organize itself, and how that organization changes stiffness. From there, the true limits of pressure become a question of whether the deepest core stays stiff or soft. Quark matter does not need to be a featureless soup because even a shared medium can organize under pressure. The early anchor is that pairing among quarks can change stiffness and transport without changing the star's calm exterior. In that region, the inner cutaway looks smoother than the outer layers. The contour rings fade into a dim core where gradients remain but borders soften. The visual anchor settles on a quiet pattern like woven shadow. It appears as faint braided bands inside the deepest zone. The braids are not separate layers. They are a hint of order in a medium that seems uniform. The first small payoff arrives with this image. If quarks pair, the medium can behave more coherently. Coherence can stiffen the response to compression. It can also reduce certain kinds of dissipation. The core can then support gravity with a different balance than ordinary nuclear matter. The first concept is color superconductivity. Color superconductivity is paired quarks moving as a coherent condensate. The definition stays brief and then returns to plain language. It is like two strands of silk twisting into a single stronger cord. It is also like mist droplets merging into a smoother sheet of fog. It matters because pairing changes which excitations are available to carry pressure and heat. The analogy stays unique and avoids earlier grooves and envelopes. It stays with silk cords and fog sheets. The braided visual anchor continues to guide the imagination. In the deepest region, the braids align with the rotation axis. They also respond to a density gradient. The braids tighten where density is higher. They loosen where density is lower. This physical detail anchors the idea that order depends on depth. Another payoff follows quickly. If pairing is strong in the center but weaker outward, the equation of state can change smoothly with radius. Smooth change helps stability. It prevents abrupt softness that would invite collapse. The scene shifts gently to a boundary region. A transition band sits between quark-rich matter and nucleon-rich matter. The band is not a cliff. It is a broad zone where properties blend. The cutaway shows it as a haze with faint speckles. The speckles represent domains with different pairing strength. The second concept is stiffness. Stiffness is how fast pressure rises with density. The definition stays short and returns to plain language. It is like how quickly a cushion stops yielding under added weight. It is also like clay that resists more as it is packed tighter. It matters because stiffness sets where the gravity can be balanced at the center. The one primary number in this section is chosen for calm scale. The central pressure can be about 10 to the power of 35 pascals. It is like stacking the weight of an ocean on each square centimeter and is still needing more. The comparison stays vivid and simple. It makes clear why the medium must be unusual. Ordinary solids and liquids have no reference point for such load. Another payoff arrives from that load. At pressures this high, small changes in microphysics can produce large changes in radius. A slight increase in stiffness can keep the star larger and more stable. A slight decrease can shrink the radius and push the star toward collapse. The braided visual anchor returns. The braids are drawn as faint currents of order in the deepest dark. They remain steady. They suggest that pairing can create a structured response even without sharp layers. A scale shift keeps the rhythm gentle. Pairing is a microscopic arrangement among quarks, yet its influence extends across kilometers of core. A tiny energy preference becomes a global support system. The cutaway widens to the outer shell. The surface rim of bent light remains unchanged. Light behaves as if it wraps around the limb and escapes with a redder tone. The outside is calm and simple. The inside is where the rulebook changes chapters. Another visual anchor appears to maintain cadence. The transition band looks like a soft cloud ring around the deepest zone. The ring is not luminous, it is a contour of behavior. Within that ring, the braided pattern fades. Outside it, the medium becomes more like a neutron superfluid. Another payoff follows. If the deepest core pairs strongly, the coupling between layers can shift. Transport of heat and momentum can slow in some channels and speed in others. This affects how the star cools over long times. It also affects how oscillations damp. The story stays calm and avoids technical lists. It remains a path through consequences. The limit of intuition arrives with the idea of superconductivity without wires or metals. Everyday superconductors are tied to electrons and materials. Here the pairing occurs among quarks in dense matter. The intuition fails because the carrier is not an electric current in a lattice. It is a change in available excitations in a quantum medium. The limit of observation follows and names its boundary. No surface measurement can directly identify color superconductivity. The interior state must be inferred through global properties like mass and radius. It also must be inferred through long-term thermal evolution. Those inferences depend on models of the crust and envelope. They also depend on uncertain microphysics. Different pairing patterns can mimic each other in outward behavior within observational uncertainty. That is a concrete limit on discrimination rather than a lack of imagination. Another payoff follows from facing that limit. Instead of seeking a single label, the task becomes bounding stiffness across density ranges. Pairing becomes one mechanism that can move stiffness upward without needing new particles to appear. It becomes a way to reconcile stability with the possibility of deconfinement. The braided visual anchor remains the quiet symbol of that reconciliation. It is order in a place that seems too extreme for order. The section eases toward a soft close. If pairing stiffens the deepest core, the star can resist collapse at higher masses. If pairing is weak or absent, the core may soften over a critical range. The next step is to examine how pressure and gravity approach a final threshold. From there, the true limits of pressure become a question of when support fails and what collapse means in calm physical terms. The deepest pressure limit shows itself most clearly when gravity and stiffness negotiate a final balance. The early anchor is that a stable neutron star exists only while the inner equation of state stiffens fast enough to halt further compression. In that region, the cutaway looks like a dark well with softened contours. The contour rings compress toward the center and then fade. The visual anchor settles on a quiet, narrowing throat. It is a region where equal density surfaces crowd together. The crowding forms a tight bundle of rings like many faint halos stacked close. This image answers a key question. The true limit of pressure is not a single number. It is the point where adding central density no longer increases support efficiently. The first concept is maximum mass. Maximum mass is the largest stable mass for a given equation of state. The definition stays brief and then returns to plain language. It is like the last safe load a shelf can carry. It's also like the final height a sandpile can hold before slumping. It matters because beyond that point stability fails even if the surface looks calm. The analogy stays unique and avoids earlier mattresses and cushions. It stays with shelves and sand. The cutaway gives physical detail for this limit. The inner rings crowd and the gradient steepens. The outer layers remain smoother. The boundary between them becomes a kind of hinge in behavior. A small payoff arrives. Stability depends on the whole profile, not only on the center. If the core softens in a band, gravity can exploit that band like a weak seam. If the core stays stiff through that band, support remains distributed. The second concept is compactness. Compactness is mass packed into a small radius. The definition stays short and returns to plain language. It is like how heavy a stone feels for its size. It is also like a dense fruit that sinks deeper when placed on soft ground. It matters because compactness strengthens gravity's grip and bends light more. The one primary number in this section anchors compactness calmly. The escape speed at the surface can be about half the speed of light. It is like trying to climb out of a deep canyon while the ground pulls steadily. The comparison stays simple and avoids symbols. A payoff follows from this speed. When escape speed is so high, the star's surface time runs slower than faraway time. Signals from the surface carry this slowdown outward. This makes timing a natural probe of compactness. Another visual anchor appears to keep the cadence even. Light behaves as if it skims the surface and curves around the limb. The rim looks thin and steady. The shadow disk looks slightly larger than its physical radius because light paths are bent. This physical detail matters. It shows that gravity is strong enough to distort the simplest geometry. Another payoff arrives. Strong bending means the star's size and mass are linked tightly by the equation of state. A stiff interior yields a larger radius for the same mass. A softer interior yields a smaller radius. Near the maximum mass, small softening has a large effect. The tight bundle of inner rings becomes the visual shorthand for this sensitivity. A scale shift keeps the narration gentle. The maximum mass is decided by microphysics deep in the core. It is decided by how pressure grows when density rises. Yet the outcome is a macroscopic threshold that can be read from afar as a population boundary. Stable stars exist below it. Beyond it, stable stars do not persist. The cutaway now holds on the narrowing throat region. The rings crowd until they nearly merge. The image suggests that the star is running out of structural room. The next small payoff clarifies what failure means in calm terms. Failure is not a surface shattering. It is the inability of pressure to rise fast enough with density. Gravity then has no counterbalance. The collapse proceeds inward. The outer layers follow because they lose support from below. The story stays quiet and avoids dramatic phrasing. The focus remains on a stability criterion. The limit of intuition arrives here with a specific point. Everyday materials fail because they crack or melt. Here the failure is global and geometric. It is a change in the balance of space-time curvature and pressure. Ordinary intuition fails because there is no familiar object that turns into deeper curvature when squeezed. The limit of observation follows and names its boundaries. Maximum mass cannot be measured by peering into a single star. It must be inferred from the heavier stable stars that exist. It must also be inferred from how mass and radius pairs cluster. These inferences depend on distance estimates and emission models. They also depend on assumptions about surface composition. Uncertainties in those models blur the boundary. Different equations of state can produce similar mass-radius relations within observational error. That degeneracy is a concrete limit on identification. Another payoff follows from that limit. Even without perfect certainty, any equation of state must avoid predicting instability for stars that clearly persist. The mere existence of heavy stable stars rules out excessively soft cores. The existence of relatively small radii rules out excessively stiff cores. The space between these constraints is where quark matter and pairing must fit if they exist. The visual anchor returns to the throat of crowded rings. The throat can be imagined as the place where the rulebook is most tested. If quark matter softens too much, the throat tightens and the star crosses the boundary sooner. If pairing stiffens the deepest region, the throat remains wider, and stability extends to higher masses. The section keeps the cadence with another scene. The outer crust remains a thin shell. The inner reservoir remains dark and smooth. The transition zones remain hazy rather than sharp. The overall sphere remains calm. Yet the internal balance is precise. Tiny changes in stiffness determine whether the star holds its shape for millions of years or whether it yields. The closing transition stays gentle. The next step is to connect this limit to slow observable consequences like cooling and long-term relaxation. From those consequences, the interior's hidden chapters can be narrowed without forcing the story into sharp certainty. A neutron star cools in silence, and that slow fading carries hints about what lives in the core. The early anchor is that cooling rate depends on which particles and paired states can carry energy away. At this distance, the star is still a dark sphere with a thin rim of bent light. The cutaway reveals a layered interior. The crust remains a stiff shell. Below it, the fluid region darkens with depth. The visual anchor settles on a temperature front. It appears as a soft curved surface inside the star. The front moves inward over time like a dim tide line. It is not a sharp wall, it is a gentle gradient where the interior becomes more uniformly cold. The first small payoff arrives with the simplest link. If the core has many active channels for energy loss, the temperature front moves quickly. If the core has paired states that suppress those channels, the front moves slowly. Cooling becomes a probe of microphysics without needing direct access. The first concept is neutrino emission. Neutrino emission is energy carried away by weakly interacting particles. The definition stays brief and then returns to plain language. It is like heat leaking through an almost invisible vent. It is also like a whisper that escapes through a thick door. It matters because neutrinos can remove energy from deep layers that light cannot reach. The analogy stays unique and avoids earlier vents or machines. It stays with whispers and hidden leaks. The cutaway shows the core as the primary source region. The density contours remain faint. The temperature front cuts across them like a slanted sheet. This physical detail matters. It shows that cooling is not uniform at first. It is shaped by gradients in density and by the availability of emission process. Another payoff follows. If a quark-rich region exists, it can change neutrino emission rates. If strong pairing exists, it can reduce available excitations and slow emission. The star's thermal history therefore becomes a contest between opening and closing channels. The second concept is pairing gap. Pairing gap is the energy needed to break a paired state. The definition stays brief and then returns to plain language. It is like the extra effort needed to pull apart two magnets. It is also like a zipper that resists opening until a threshold is reached. It matters because a large gap suppresses many low-energy processes. The cutaway image adds a new physical detail. A thin band near the transition region glows slightly in illustration. The glow marks where pairing strength changes with depth. Above the band, pairing may be weaker. Below it, pairing may be stronger. The temperature front meets this band and bends. It curves as if guided by a softer layer. Another payoff arrives from that bend. A bend in the temperature front implies a bend in heat capacity and emission efficiency. The front does not simply march inward, it adapts to internal structure. This gives a path to distinguish broad classes of interiors. The one primary number in this section anchors time. The most rapid neutrino-dominated cooling can shape the first 10,000 years. It is like a long winter compared with a single day. The comparison is immediate and calm. After that early era, surface photon cooling becomes more important. The narrative stays gentle. A scale shift follows naturally. A small change in pairing energy at the particle level can alter the star's temperature over thousands of years. Microscopic gaps shape macroscopic time. The visual anchor returns to the moving front. The front is drawn as a curved sheet that slowly settles deeper. Above it, the crust stays slightly warmer. Below it, the core becomes uniformly cold. The motion is slow and quiet. It resembles fog settling into a valley at night. The physical detail is the smoothness of the gradient rather than a sharp step. That smoothness suggests diffusion of heat through dense matter. Another payoff follows. A superfluid core has reduced heat capacity and altered transport. Reduced heat capacity means less stored energy for a given temperature. Altered transport means the front can sharpen or broaden depending on scattering. The star's cooling therefore encodes both capacity and conductivity. The limit of intuition appears softly. Everyday cooling is controlled by air and radiation. Here, cooling is controlled by particles that barely interact. The interior can lose energy without glowing brighter. This breaks the expectation that hotter means more visible. The star can cool rapidly while remaining dim and quiet. The limit of observation follows and names its boundary. The interior temperature cannot be measured directly. Only surface emission can be seen, and even that depends on surface composition and magnetic effects. The inferred surface temperature depends on models of the thin outer layers. Those models have uncertainties. These uncertainties blur the mapping from surface signal to core temperature. Different combinations of core emission and surface insulation can produce similar observed cooling curves. That degeneracy is a concrete limit on inference. Another payoff follows from accepting that limit. Instead of claiming a unique core composition, cooling can set bounds. It can rule out cores that cool far too fast. It can also rule out cores that cool far too slowly. Within those bounds, pairing and quark matter remain possibilities that must be consistent with the observed pace of fading. The visual anchor becomes more detailed to keep cadence. The temperature front meets a density contour ring and slides along it for a while. The slide suggests that some layers conduct heat more easily. The front then crosses into a deeper zone and becomes smoother. This illustrates how transport and emission compete. A signal would carry the outcome outward as a changing surface spectrum, yet the signal is filtered by the crust and atmosphere. The story remains calm and precise. Another payoff arrives from the time scale. Over tens of thousands of years, the star approaches an isothermal interior. Once that happens, the details of core emission matter less for the overall gradient. They still matter for how quickly energy leaves. The interior becomes a single reservoir with a slow leak. The leak rate is set by which processes remain available at low temperature. Pairing can close many of them. Unpaired components can keep some open. The section closes with a gentle transition. Cooling suggests which degrees of freedom remain active in the core. The next step is to connect this thermal story to mechanical relaxation and oscillations. From that connection, the hidden stiffness and phase structure can be narrowed without needing direct images. A neutron star can ring and settle, and the way it relaxes can hint at hidden softness or stiffness deep inside. The early anchor is that oscillations and damping depend on the core's phases and on how easily layers exchange momentum. At this distance, the star remains a dark disk with a thin curved rim of light. The cutaway shows the crust as a rigid shell. Beneath it, the interior appears as a smooth reservoir with faint contour rings. The visual anchor settles on standing wave bands inside the star. They look like pale, evenly spaced arcs that sweep through the cutaway. The arcs are not sound in air, they are density and pressure waves in dense matter. The first small payoff arrives in a direct link. A stiffer core tends to ring at higher frequencies. A softer core tends to ring at lower ones. This changes the timescale of relaxation as well. The first concept is oscillation mode. An oscillation mode is a global pattern of vibration in the star. The definition stays brief and returns to plain language. It is like a bell's preferred tone. It is also like a rope that chooses certain standing waves when plucked. It matters because each mode samples different depths and stiffness. The analogy stays unique and avoids Early-Earth shelves and sand. It stays with bells and ropes. The cutaway image adds physical detail. Some arcs concentrate near the crust base. Other arcs extend through the deep core. Where arcs crowd together, the gradient is steep. Where arcs spread out, the medium is more uniform. Another payoff follows. Because different modes live in different regions, a set of modes can separate crust effects from core effects. The story remains calm and does not demand perfect identification. It follows the idea of layered sampling. The second concept is damping. Damping is the loss of oscillation energy into heat or radiation. The definition stays brief and returns to plain language. It is like ripples on a pond fading into stillness. It is also like a slow sway that stops as energy spreads into many small motions. It matters because damping reveals how strongly the interior resists shear and how quickly energy leaks into other channels. The visual anchor returns to the standing arcs. Some arcs remain sharp, some blur as time passes. The blur indicates damping. The blur is not uniform. It is stronger in specific bands where the medium changes phase or where coupling is strong. The physical detail is a haze ring near a transition zone. The ring marks a place where waves scatter. Scattering changes the wave pattern. It can convert coherent motion into many smaller excitations. Another payoff arrives. A transition band that mixes phases can act like a rough coastline to a wave. It reflects part of the motion. It transmits part. It also breaks part into smaller scales. This increases damping without needing violent processes. The one primary number in this section anchors the timescale in calm language. A strong oscillation can settle in about a minute. It is like a slow breath compared with a heartbeat. The comparison is immediate and quiet. This minute scale is short compared with cooling ages, yet it is long enough to carry information about internal friction and coupling. A scale shift follows gently. The wave period can be milliseconds. The envelope of damping can be tens of seconds. Both arise from microphysics in a region smaller than a dust grain. Yet the motion spans an object tens of kilometers wide. Microscopic viscosity and pairing gaps shape a macroscopic settling. The cutaway widens to show the outer rim of bent light. Light behaves as if it skirts the surface and returns a thin halo. That halo remains unchanged while the interior rings. A signal would carry changes outward through timing and through any associated radiation. The story stays careful about what can be observed. Another visual anchor appears to keep cadence steady. A faint node line crosses the cutaway where motion is minimal. On one side of the line, the density increases slightly. On the other side, it decreases slightly. The node is a physical structure in the wave pattern. It helps identify where the mode samples the star most strongly. Another payoff follows from node placement. If nodes sit deeper, the mode is sensitive to core stiffness. If nodes sit shallower, the mode is more sensitive to crust and outer layers. This allows a gentle separation of influences. The section now touches the limit of intuition. Waves in dense matter do not behave like waves in air. The medium is relativistic and strongly interacting. Shear and bulk responses can be unfamiliar. Some layers can flow almost frictionlessly. Others can behave as elastic solids. This breaks the simple idea of a single speed of sound and a single damping rate. The limit of observation follows and names its boundary. Oscillation modes are difficult to identify uniquely from distant signals. The signals can be weak, they can overlap, they can be filtered by magnetospheric processes not modelled perfectly. Even when a frequency is measured, mapping it to a specific mode requires assumptions about mass and radius. Those assumptions carry uncertainties. Different interior models can reproduce similar frequency sets within error bars. That degeneracy is a concrete limit on inference. Another payoff follows from accepting that limit. Mode information still constrains combinations. It can rule out interiors that would damp too quickly. It can rule out interiors that would leave long-lived ringing incompatible with calm behavior. It can also connect to the equation of state by relating frequency to compactness. The visual anchor returns to the arcs fading into stillness. The star settles back into a quiet equilibrium. The contour rings regain their smooth spacing. The haze ring near the transition zone remains as a reminder. The interior can contain boundaries that are not sharp, yet those boundaries influence how motion is shared and lost. The closing transition stays soft. The next step is to widen perspective from individual ringing to long-term rotational evolution and stability. From that wider view, the interior's softness and stiffness can be bounded by how the star remains steady over immense spans of time. Rotation looks steady from afar, yet it is a slow ledger of how stiffness and coupling share motion across layers. The early anchor is that long-term spin evolution depends on where angular momentum is stored and how easily it leaks between crust and core. At this distance, the star remains a dark point with a thin rim of curved light. The cutaway shows the crust as a rigid shell and the interior as a smooth reservoir. The visual anchor settles on concentric drift lines. They appear as faint spirals inside the cutaway, not on the surface. The spirals are a way to visualize differential rotation. The lines are closer together in some bands. They spread out in others. This spacing is a physical detail tied to shear. The first small payoff arrives with a simple statement. When coupling is weak, different layers can carry slightly different rotation rates. When coupling is strong, layers stay nearly locked. The star's spin history therefore becomes a record of internal friction and phase structure. The first concept is angular momentum. Angular momentum is rotational inertia carried through motion and distribution. The definition stays brief and returns to plain language. It is like the steadiness of a spinning top that resists being slowed. It is also like a flywheel effect without a wheel. It matters because the star can hide large reserves of spin in its fluid layers. The analogy stays unique and avoids earlier ropes and bells. It stays with tops and steady spin. The cutaway shows the drift spirals as slow-ordered patterns. Near the crust base, the spirals tighten. Deeper down, they relax. The gradient of spacing reflects changing coupling. Another payoff follows. A tighter spiral near the crust implies the crust and adjacent fluid stay closer in rotation. A looser spiral deeper down suggests a reservoir that can lag or lead slightly. This reservoir can exchange momentum over long times. The second concept is relaxation timescale. Relaxation timescale is how long a difference in rotation takes to fade. The definition stays brief and returns to plain language. It is like how long a stirred pond takes to become still. It is also like how long a stretched rubber band takes to stop vibrating. It matters because different interior phases set different timescales. The visual anchor returns to the spiral bands. A narrow band shows a subtle kink where spirals change pitch. That kink marks a transition zone. It could be where entrainment strengthens. It could be where a quark-rich region begins. The kink is not a sharp step. It is a smooth change in shear response. Another payoff arrives. A smooth kink allows gradual transfer of angular momentum rather than sudden jumps. It can explain why many stars show steady slowdown without frequent abrupt changes. The section's one primary number anchors the pace and calm time. The rotation period can be about 1 second. It is like a slow heartbeat in a quiet room. This second scale repeats for millions of years. The scale shift is gentle and clear. A 1 second rhythm persists across ages longer than recorded history. That persistence means tiny internal drifts matter. A drift of a fraction of a turn per day would add up over years. Yet the star remains stable because the interior mediates those drifts. The cutaway shows a faint boundary ring where the spiral pitch changes. That ring is the main visual anchor. It is a ring of shear. It is not luminous. It is a contour of behavior. Light behaves as if it bends around the surface and leaves a thin rim unchanged by the internal spirals. A signal would still carry rotation outward through timing. Another payoff follows from that. Timing measurements can track spin with extreme precision. This makes rotation a sensitive probe of slow internal exchange. The story stays careful about what can be inferred. The limit of intuition appears with a specific point. In everyday objects, rotation slows because of air drag and friction at contacts. Here there is no air and no bearings. Spin changes because electromagnetic torque acts on the exterior, and because internal coupling shares the response. Ordinary intuition fails because the dominant pathways are not familiar mechanical contacts. The limit of observation follows and names its boundary. Internal drift spirals cannot be observed directly. Only changes in rotation period can be measured. Interpreting those changes requires assumptions about external torque. It also requires assumptions about how much angular momentum sits in each layer. Different interior models can produce similar spin-down curves if torque histories differ. That degeneracy limits how uniquely coupling can be inferred. Another payoff follows from accepting that boundary. Even with uncertainty in torque, some interior behaviors are constrained. Extremely weak coupling would allow large persistent differential rotation. That would tend to produce more irregular timing than often observed. Extremely strong coupling would erase reservoirs and limit certain kinds of timing recovery. Observed stability suggests coupling in an intermediate range for many stars. The visual anchor returns to the ring of shear. The ring drifts inward slowly in the illustration. This represents changing coupling as the star cools. As temperature falls, pairing gaps can grow. As pairing grows, mutual friction channels can close. This can lengthen relaxation timescales. Another payoff arrives. Cooling can therefore change spin evolution. The thermal story and rotational story intersect. A core that becomes more paired may store rotation more cleanly. A core that remains unpaired may share rotation more rapidly. The cutaway shows the spirals becoming slightly smoother over long time. This suggests that differential rotation can diminish as coupling strengthens, or it can persist if coupling weakens. The section keeps a calm cadence with a final visual scene. The rim of light remains steady. The interior spirals fade into a uniform pattern. The ring of shear remains as a faint contour. It suggests that the star's long life is a slow negotiation between layers. The closing transition stays gentle. The next step is to widen further and connect rotation and stability to global populations of neutron stars. From that wider view, the interior rulebook can be bounded by which kinds of stars persist and which kinds do not. Some neutron stars may share the same mass and yet hide very different interiors, like two quiet stones that weigh the same but feel different in the hand. The early anchor is that a strong phase transition can create twin-stable configurations with different radii for the same mass. In that region, the cutaway does not show a single smooth ladder of density. It shows a profile that can settle into one of two gentle shapes. The visual anchor becomes a pair of dark spheres suspended in stillness. They carry the same weight. One sphere is slightly larger, the other is slightly smaller. Both have the same thin rim of curved light. Inside each contour, rings drift at different spacing. In the larger sphere, rings spread more evenly. In the smaller sphere, rings crowd more tightly toward the center. The first small payoff arrives quickly. If two stable branches exist, radius is not a simple one-way function of the mass. The outside can look similar while the inside follows a different chapter of compression. This turns the interior rulebook into a choice between routes rather than a single road. The first concept is a phase transition. A phase transition is a change of state driven by pressure. The definition stays brief and returns to plain language. It is like water turning into ice when conditions cross a line. It is also like foam turning into a denser gel under steady squeezing. It matters because it can soften the pressure response over a narrow range. The cutaway shows that narrow range is a smooth inflection. The density gradient steepens and then relaxes. The physical detail is a kink in ring spacing that does not form a sharp boundary. The kink spreads into a band. The band separates two regimes of stiffness. Another payoff follows. If the band is strong enough, gravity can push the star from one stable arrangement toward another. The star does not need to flare or break. It only needs a slow change in central conditions. The narrative remains calm and conditional. The pair of spheres holds the mind on a simple picture. One branch is puffier, the other is more compact. The second concept is stability branch. A stability branch is a range of configurations that resist collapse. The definition stays brief and returns to plain language. It is like a walkway that remains level over a stretch. It is also like a calm shelf in a steep mountain path. It matters because a star can exist only on stable shelves of the rulebook. The visual anchor returns to the two spheres and their ring patterns. In the larger sphere, the transition band sits deeper and broader. In the smaller sphere, the band sits closer to the center and is narrower. The difference is subtle yet important. Another small payoff arrives. A narrower band can make the switch between branches more abrupt in central density. A broader band can make the switch more gradual. Both possibilities shape what kinds of stable stars populate the cosmos. The one primary number in this section anchors the mass scale of interest. The heavier stable neutron stars can be about 2 solar masses. It is like placing 2 suns into a sphere not much wider than a long bridge. This comparison makes the compactness immediate without using harsh notation. It also explains why the rulebook must be stiff somewhere. Such mass gravity presses hard on every layer. If a phase transition softens too much at the wrong depth, that the stable shelf ends early. Another payoff follows from that boundary. The existence of very massive stable stars limits how deep and how soft any transition can be. If twin branches exist, the stiffer branch must return at higher density. The core must regain support after the transition. This is where quark matter and pairing can matter. They can soften and then stiffen, or they can avoid extreme softness altogether. The visual anchor shifts gently to a second scene that supports the same idea. The two spheres cast overlapping shadows in the surrounding darkness. The shadows differ in size, their mass is the same, their curvature is not the same. Light behaves as if it bends more around the smaller sphere. Its rim appears slightly more wrapped. This physical detail ties the interior choice to an outward geometry. Another payoff arrives. If compactness differs, the same mass timing signals would differ too. A signal would leave the surface with a different gravitational redshift. It would also follow different space-time paths near the limb. This means that the twin idea is not purely internal. It has outward fingerprints, even if faint. The scale shift stays gentle. The difference between branches can be set by microphysics at femtometer scales. Yet it can change the radius by a kilometer scale amount. A small change in how matter rearranges itself alters the size of an object across tens of kilometers. This is a quiet amplification. It is the same theme that appears throughout the journey. The limit of intuition arrives with a specific point. Daily experience expects that squeezing something makes it smaller in a smooth way. Here, squeezing can open new degrees of freedom. Opening can temporarily make matter easier to compress. The star can then become more compact at nearly the same mass. Intuition fails because compressibility is not fixed. It can change chapter as particles reorganize. The limit of observation follows and names its boundary. Distinguishing twins requires precise mass and radius estimates. Those estimates depend on surface emission models and distances. They also depend on assumptions about thin outer layers. Small changes in those assumptions can shift inferred radii. Population sampling adds another limit. Only a subset of stars is observed well enough to constrain radii tightly. This can hide a second branch even if it exists. That is a concrete limitation of inference from incomplete and model-dependent data. Another payoff follows from accepting that boundary. The twin idea becomes a hypothesis that can be tested in ranges rather than a single claim. If many stars cluster around similar masses but show a spread in radii, a strong transition becomes more plausible. If radii track mass smoothly with little spread, a strong transition becomes less likely. The interior rulebook is then narrowed by patterns rather than by a single measurement. The visual anchor returns to the pair of spheres once more. The larger sphere shows wider ring spacing in its core. The smaller sphere shows a tighter bundle of rings and a steeper central gradient. Both remain calm and stable in the illustration. Neither needs dramatic behavior. Their existence alone is the message. Another payoff arrives from that quietness. Stability shelves can hide different compositions without forcing new outward features. The cosmos can host diversity in interiors while keeping exteriors simple. This helps explain why interior physics remains an open field. The outside is a smooth mask. The inside is a layered negotiation between pressure and quantum structure. The section eases toward a gentle close. Twin branches link microscopic phase changes to macroscopic populations and constraints. The next step is to widen again to the longest timescales and the broadest consequences of these hidden interiors. From there, the story can settle into a calm perspective on what pressure ultimately permits. A neutron star lives a long time, and its interior slowly rearranges as temperature falls and composition settles. The early anchor is that long-term evolution can shift phase boundaries and change which core states remain possible. At this distance, the star appears as a steady dark bead against deeper darkness. The cutaway shows a crustal shell and a deep core with smooth shading. The visual anchor becomes a drifting boundary ribbon. It is a thin, curved band inside the cutaway that moves inward over ages. The ribbon marks where one phase gives way to another. It does not cut sharply. It has a blurred edge like a soft brushstroke. This physical detail matters because real interiors are likely mixed and gradual. The first small payoff arrives with a calm link. If the ribbon drifts, the star's internal stiffness profile changes with time. A star can begin with one core structure and end with another. The outside remains similar. The inside rewrites itself slowly. The first concept is chemical equilibrium. Chemical equilibrium is composition set by balance of reactions under pressure. The definition stays brief and returns to plain language. It is like a crowded room settling into a stable arrangement. It is also like ingredients in a soup redistributing until taste is uniform. It matters because equilibrium sets which particles are present at each depth. Presence controls pressure response and neutrino emission. The analogy stays unique and avoids earlier doors and zippers. It stays with rooms and soup. The cutaway shows a subtle layering. The crust is rigid. The outer core is smooth. The inner core has a darker gradient. The boundary ribbon lies between outer and inner core. Another payoff follows. If equilibrium shifts the fraction of certain particles, the ribbon can move. It can thicken or thin. A thin ribbon suggests a sharper transition. A thick ribbon suggests a mixed phase. Mixed phases can soften or stiffness over a band. They can also alter transport. The second concept is bulk viscosity. Bulk viscosity is resistance to compression when composition lags equilibrium. The definition stays brief and returns to plain language. It is like a sponge that warms and slows when squeezed repeatedly. It is also like a traffic flow that resists sudden compressions because cars need time to adjust spacing. It matters because it damps oscillations and affects stability during rotation and vibration. The visual anchor returns to the ribbon. The ribbon is drawn with tiny ripples along its edge. These ripples represent slow adjustment. They are not waves on a surface. They are local regions where reactions catch up or fall behind. Another small payoff arrives. If reactions are fast, composition tracks compression smoothly and damping is mild. If reactions are slow, compression drives the system out of balance and damping grows. This provides a route from microphysics to long-term spin and mode behavior. The one primary number in this section anchors the timescale of deep adjustment. Equilibrium changes can unfold over about 1 million years. It is like a coastline reshaped by gentle tides rather than a storm. The comparison keeps the tone soft. A scale shift follows naturally. The same star rotates in seconds. It cools in thousands of years, yet composition can drift over 1,000,000 years. Tiny reaction rates at the particle level set the pace of that drift. The interior is therefore a clock with many hands. The cutaway widens and the ribbon is seen as an arc that hugs a certain density contour. As time passes, the arc slides inward by a small amount. The physical detail is the way the arc follows a contour rather than cutting across it. This suggests that pressure and density structure guide where phases prefer to exist. Another payoff follows. A phase that is favoured only above a threshold density will occupy a central volume. As the star cools and equilibrium shifts, the threshold can change. The volume then expands or contracts. That changes the star's stiffness profile. It also changes which emission processes are active. The narrative stays calm and avoids dramatic transitions. The limit of intuition appears with a specific point. Everyday phase changes are driven by temperature alone. Here, pressure dominates and temperature modulates the details. A small change in temperature can shift pairing gaps. Those shifts can open or close reaction pathways. This is unfamiliar because the medium is quantum and degenerate. Intuition fails because the usual idea of heat as a dominant driver does not apply. The limit of observation follows and names its boundary. The ribbon cannot be seen. Only indirect proxies exist, such as cooling curves and timing noise. Interpreting those proxies requires models of surface layers and external torques. It also requires assumptions about interior reaction rates. Those rates are uncertain. Different combinations of equilibrium composition and transport can reproduce similar long-term observations. That degeneracy is a concrete limit on pinning down the ribbon's motion. Another payoff follows from accepting that boundary. Even without direct sight, the ribbon's possible positions can be bounded. If long-term behavior shows strong damping of certain oscillations, bulk viscosity must be sufficient in relevant layers. If spin evolution remains smooth coupling, must avoid large persistent differential rotation. These constraints carve away parts of parameter space. The ribbon becomes a tool for organizing that space rather than a single predicted curve. The visual anchor deepens with a new scene while staying consistent. The ribbon is shown as a pale band that slowly tightens around the center like a soft belt. It tightens without snapping. This image conveys a gentle migration of phases under changing conditions. Another payoff arrives. Gentle migration avoids sudden structural upheaval. It allows stars to age quietly while still changing internally. This quiet change is important for the larger question of pressure limits. The limit is not only a static maximum mass, it is also a set of evolving conditions that decide which phases exist at which times. The section closes with a soft transition. Long-term evolution ties together cooling reaction rates and phase structure. The next step is to widen to consequences that span the full population and the deepest time. From that wide view, the story can approach a calm resolution about what the universe permits inside these compact spheres. A limit is not only a number in a table, it is a quiet boundary where stability ends and compression cannot find a new resting shape. The early anchor is that the true pressure limit is expressed as the maximum stable mass and as the steepness of the interior rulebook at the highest densities. At this distance, the star is a dark point with a thin lensing rim. The cutaway shows a core shaded from pale to deep grey. The visual anchor becomes a pressure staircase carved into the shading. It is not a literal staircase. It is a sequence of tight contour steps near the centre. Each step is a place where a small change in radius corresponds to a large change in pressure. The steps crowd together as depth increases. This is a physical detail tied to the gradient of support. The first small payoff arrives at once. The limit appears where the steps crowd so tightly that no new step can hold. Beyond that, a stable configuration does not exist. The star cannot remain a neutron star on that side of the boundary. The first concept is equation of state. An equation of state is the relation between pressure and density. The definition stays brief and returns to plain language. It is like a rulebook that tells how firm a cushion becomes when pressed. It is also like a map from squeeze to resistance. It matters because it decides whether added weight can be supported or leads to collapse. The analogy stays unique and avoids earlier bells, belts, soup and tops. It stays with cushions and firmness. The cutaway keeps the pressure staircase visible. In the outer core steps are wider. In the inner core steps tighten. A thin transition band appears as a step that is slightly flatter than its neighbours. That flatter step represents a softening. It can be due to a phase change. Another payoff follows. A brief softening does not always destroy stability. If stiffness returns at higher density, the staircase continues upward. If stiffness does not return, the staircase ends early. The second concept is maximum stable mass. Maximum stable mass is the highest mass that remains stable as a neutron star. The definition stays brief and returns to plain language. It is like the heaviest stack a shelf can hold without bowing. It is also like the last brick that can be placed before a gentle arch gives way. It matters because observed heavy stars demand a stiff rulebook at some depth. The one primary number anchors this demand. The maximum stable mass must reach about 2 solar masses. It is like 2 suns held inside a sphere not much wider than a long bridge. This comparison repeats the mass value but uses a new everyday image. It avoids earlier phrasing by shifting the object. Another payoff arrives. Because the limit reaches that scale, the core cannot remain too soft for too long. If quark matter appears, it must not behave like an overly compressible fluid at the highest densities. It must have a mechanism that restores pressure efficiently. Pairing, repulsion and strong interactions can provide that restoration. The story stays careful and does not claim certainty. It frames a constraint rather than a verdict. The visual anchor now shifts gently to a slow cross-section sweep. The sweep moves from the surface inward. The shading deepens. The contour steps tighten. Near the center, the steps form a compact cluster like close rings in a tree trunk. This is the main visual anchor. It is unique across the script. Another payoff follows from this tree ring image. In a tree, tight rings reflect slow growth or harsh seasons. In the star, tight contour steps reflect extreme compressibility limits and strong gravity. The outer layers contribute volume. The inner layers decide stability. The scale shift stays soft. The microphysics of particle interactions sets the slope of the rulebook. That slope determines whether an object tens of kilometers across can exist for millions of years. A change at femtometer scales decides the fate of a structure that can be tracked across galaxies. Light behaves as if it traces the star's curved space-time and produces a rim that remains steady. A signal would carry information about mass and radius through timing and spectral shifts. Yet the inside remains hidden. The limit of intuition arrives with a specific point. In daily life, adding weight to a support often gives warning through bending. Here the warning is subtle. The star can remain apparently stable while the central region approaches a tipping point. The reason is that stability is global. It depends on how pressure integrates through the interior. A local softness can be compensated by a stiffer layer above. Intuition fails because support is not a simple local property. The limit of observation follows and names its boundary. The equation of state at the highest densities cannot be measured directly. Mass measurements can be precise. Radius estimates have larger uncertainties and depend on emission models. High-density behavior beyond a few times nuclear density must be inferred through modeling. Different rulebooks can fit current mass constraints. They can also fit limited radius data within errors. This makes the pressure staircase near the center uncertain. The tightest steps are the least observable. Another payoff follows from accepting that boundary. The limit can still be narrowed by combining independent constraints. Heavy masses demand stiffness. Cooling behavior constrains composition and pairing. Oscillation damping constrains viscosity and coupling. Rotational stability constrains angular momentum reservoirs. Each constraint trims a different part of the rulebook. Together they reduce the space of possible staircases. The visual anchor returns to the center cluster of steps. A single flatter step is shown as a gentle plateau. The plateau represents a phase transition. It is surrounded by steeper steps that return stiffness. This shows how a core can change composition without losing the ability to support weight. Another payoff arrives. The true limit is therefore not only a maximum mass, it is also a requirement of recovery. Any softening must be followed by a firm response at higher density. Otherwise, the star cannot reach the observed masses. The section eases toward a quiet close. The pressure staircase remains the central image. The steps do not climb forever. They end where stability ends. The next step is to soften the tone further and gather the journey into a calm resolution. From that closing perspective, the interior becomes less a mystery and more a quiet landscape of constraints. The deepest core remains unseen, yet its limits leave a calm signature in what a neutron star can remain. The early anchor is that pressure reaches a final balance only when stiffness and gravity match, and that balance has a gentle edge. At this distance, the star sits in darkness with a faint lensing rim that curves the background light. The cutaway returns one last time. It shows a smooth sphere with a central gradient that darkens towards the middle. The visual anchor becomes a quiet field of contour bands. These bands look like layered fog in a hollow, each layer slightly denser than the last. Near the center, the fog bands narrow into a soft knot. The knot is not sharp. It is a rounded core of shading where the gradient steepens. This physical detail carries the idea of compression without needing numbers. The first small payoff arrives at once. A limit is not a dramatic wall. It is a place where the fog bands can no longer crowd closer without changing the rules. Stability ends when further compression would require an impossible response. The first concept is compressibility. Compressibility is how much density changes when pressure increases. The definition stays short and returns to plain language. It is like a dune that settles under steady wind. It is also like a pile of dry sand that firms as grains lock together. It matters because low compressibility allows pressure to rise quickly and hold up weight. The cutaway shows the dune idea without any landscape. The fog bands represent grains finding tighter packing. Another payoff follows. When compressibility is low, the core can resist added mass without shrinking too much. When compressibility is high, the core shrinks easily and gravity gains the advantage. The second concept is phase boundary. A phase boundary is the region where one core state gives way. The definition stays brief and returns to plain language. It is like a shoreline where wet sand becomes dry sand. It's also like a slow blend where two textures mingle over a distance. It matters because boundaries can soften the interior for a while. They can also provide new ways to carry heat and momentum. In the cutaway, one boundary appears as a faint ring of intermediate shading. The ring is not a line, it is a band with a blurred edge. Another small payoff arrives. A blurred boundary suggests coexistence. Coexistence allows the interior to change without a sudden jump. It also spreads the effect of any softening. A star can then keep a stable global shape even while the center evolves. The scale shift arrives in a quiet step. Coexistence happens in layers thinner than a grain of dust. Yet it influences the sphere about 20 kilometers across, like the length of a small island. The same layer also shapes behavior over millions of years as the interior cools. The fog bands linger and drift at an almost invisible pace. Light behaves as if it skims a curved path near the surface and the rim remains steady. A signal would carry the mass and compactness as a global summary. Yet the knot of fog at the center remains beyond direct reach. Another payoff follows from that separation. Because the center is hidden, the best understanding comes from constraints that agree. A heavy mass narrows how soft the rulebook can be. Cooling narrows which particles can dominate. Damping narrows how quickly composition can adjust during motion. Each line of evidence is incomplete. Together they form a calmer picture of what cannot happen inside. The limit of intuition arrives with a specific point. In ordinary solids, stiffness often rises smoothly with pressure. In these cores, new degrees of freedom can appear and soften the response. That softening can be temporary. It can be followed by a return of stiffness at greater density. Intuition fails because the material is not a lattice of fixed units. It is a quantum fluid where the population of particles can change. The limit of observation follows and names its boundary. The center cannot be imaged. Mass measurements can be accurate for some systems. Radius information is harder and model dependent. Cooling signals are filtered through uncertain surface layers. Oscillation signatures can be weak and ambiguous. This means several different interiors can produce similar outer behavior. The degeneracy is a real limit on inference. Another payoff comes from accepting that limit without frustration. Degeneracy can be organized rather than feared. It suggests families of interiors that share a similar compressibility profile. It suggests which kinds of phase boundaries are allowed and which are excluded. It also suggests which microphysical mechanisms are necessary if exotic matter is present. The fog bands in the cutaway become a guide to these families. Wide bands represent gentle gradients and strong stiffness. Narrow bands represent rapid changes and a delicate balance. The third concept is stability. Stability is the ability to return to equilibrium after disturbance. The definition stays short and returns to plain language. It is like a bowl that brings a rolling bead back to the lowest point. It is also like a calm basin that smooths ripples after a brief shake. It matters because stable stars persist as neutron stars. Unstable ones do not remain in that state. The visual anchor now shifts to the basin image inside the cutaway. The contour bands are shaped like shallow nested bowls centered on the knot. A small payoff follows. If the inner bowl remains deep enough, small disturbances settle. If the bowl flattens too much, disturbances do not return cleanly. The boundary between deep and flat bowls is the quiet edge of the pressure limit. This phrasing avoids sharp drama. It keeps the tone steady. Another scale shift follows. The bead in the bowl corresponds to oscillations that last seconds. The bowl shape corresponds to an interior rule set by interactions at tiny scales. The persistence of the bowl corresponds to ages that outlast many stellar lifetimes. The story therefore resolves as a bridge from the smallest to the largest. The fog bands continue to drift in slow time. A phase boundary can move as temperature falls and equilibrium shifts. That movement can tighten or loosen the central knot. It can also change how the core shares momentum with outer layers. Yet the outside remains a calm sphere. The rim of bent light remains smooth. Another payoff arrives in the calm conclusion. The true limits of pressure are not a single dramatic threshold. They are a set of requirements that must hold together. Pressure must rise fast enough with density. Any softening must be brief or compensated. Boundaries must not erase stability. The allowable interiors are those that satisfy all constraints at once. The cutaway gently fades from the knot outward. The fog bands broaden. The shading becomes almost uniform. The lensing rim softens until it is only a faint curve. This final visual anchor suggests a soft landing. The hidden core remains complex. Yet its influence is simple in outcome. A stable neutron star exists within a narrow window of possibilities. The section closes with a quiet forward motion. Beyond the limit, another compact state would be required. Within the limit, the star remains as a steady point. The journey now rests on that steadiness and lets the darkness become still.